You're great.
Hey, Mom, good one.
Yeah. Okay, so CO5 and CO6, we're going to do them all in one shot. I don't see us making it through this entire lesson and the Explore today. Maybe not even tomorrow. Okay? So, we're starting off with this first, and then we will do the Explore in between reflections and dilations. So we're going to start with reflections. Reflections is just how it sounds. I go stand in a mirror and I see my what back? Which is my reflection. So reflection is very simple. I'm going to go with 4th or 5th grade. I can't remember what standard it's in. You learn a thing called the line of symmetry. Does anyone remember what the line of symmetry means? It reflects down the middle. The specific line of symmetry means that I could fold it along that line and it would match up. So like, barring any imperfections or somebody has 2 different colored eyes or anything, our body has a line of symmetry right down the center. If I folded my body together, it would match. Okay? A heart has a line of symmetry, right? Some objects could have multiple lines of symmetry. What shape would have an infinite number of lines of symmetry? Circle. Circle. Okay. Square has how many lines of symmetry? 2. Okay. So that's what it is. We can fold it, and that's kind of like what a reflection is going to be. So looking at this picture, do you see a line of symmetry for the picture? Which axis is the line of symmetry? X or Y?
Y.
The y-axis is a line of symmetry. If I folded it along this y-axis, would these 2 match up? Yeah. Now, what about the x-axis there? It wouldn't work, right? This one only has a line of symmetry down the y. Okay? So, here's our rule. Look at the bottom. If f of x and the f is switched to the negative, we're going to reflect it over the x-axis. If the x is negative, that means we're affecting the x number. That's why it reflects over the y-axis. So do you see that my number was x, or 3, and now it's negative 3? And my x was affected, because it's showing me my x was affected. If I reflect it over the y, my f is affected because the whole f of x is affected. And it'll make more sense once we get into it. Did you write this? I would if I were you. Or just choose to ignore me and flip the page.
I didn't know you every time.
Okay, here we go. So this is saying f of negative x. That's all it's saying is switch it to its opposite. It is negative 3 right now. So how do I change this x to its opposite? What should it be now?
Positive.
So this is really going to switch to a positive 3. And my other dots move over with it. This was negative 4, 3, so it's going to be positive 4, 3. Negative 2, 3, positive 2, 3. So which axis did I reflect it over? The x or the y?
Y.
The y. I reflected it over the y-axis. What questions do you have on the first one I did? Okay, let's take a look at B. Which one's switching to its opposite? The f of x or just the x? The f of x. So I'm reflecting it over the x-axis. Okay? So how would that look? Is this guy going to move? This is your x-axis, and I'm reflecting it over, so I want my line of symmetry to be the x-axis. Is this point going to move? No. These points, if it was over -4, up 3, what's it going to be now? -4, 3. And I apologize, those are very hard lines to see. So just get close. 2, -3. That's probably more up there. Because we were changed our y's to their opposite. This was -4, 3. This is now -4, -3. We changed the y's to their opposite because that's what it told me to do. This is as extensive as we're going to get on reflecting. Your main thing you have to remember is when it says -f of x, I'm reflecting it over the x. When it says f of -x, we're reflecting it over the y. Okay? I'm going to have you guys try this one. The points are still pretty close to the same. This here is -4, 3. This is -2, 3. Same down here, -4, 3, -2, 3. And then these are -3, 1. I have orange all over my desk. No, it's got to reflect over this. It's one spot away. You got to do it down here. 2 more down. Yeah, because it goes into our dilation. Okay, here we go. Reflect over g of -x. So I'm reflecting over the y or over the x? I'm reflecting over the y. So it was -3, 1. Now it's going to be +3, 1. It was -2, 3. Now it's going to be 2, 3. It was -4, 3. It's now going to be 4, 3. So all my x's changed. That's why it says this. Change your x to its opposite. That's why it ends up reflecting over the y-axis. All right, now this guy. I kind of wrote my number in the way. I'm changing all my y's to their opposite. So it was -3, 1. Now it's going to be -3, -1. It was -4, 3. It's going to be -4, -3. It was -2, 3. It's going to be -2, -3. Yes, my lines are longer. Okay.
I handed you out an explore. We're going to go ahead, because you can see here, we're going to switch to dilation. That's all reflection is. Okay, here we go. When stretching or shrinking a function vertically, the x values in the function do not change. Complete the table below, or complete the table of values for the function f of x equals x squared. So what is negative 2 squared? Positive 4? What is negative 1 squared? 0 squared? 1 squared. And 2 squared. Since it has this squared function in it, we already know what it's going to look like. What's it going to look like? A u, because it's what type of function? Quadratic. Good. All right, so now what we're going to do is we're going to graph this. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. Has this already looked like something we've graphed before? Yes? Okay. This is known as a quadratic graph because it looks like a U. How can we tell just from the equation that it's a quadratic graph?
It's squared.
It's squared. Yes, I'm going to let you work with graphing calculators again today. Right over here. I was running out of colors. Okay. All right, so this right here, what we're going to call this table that we just did, is we're going to call that our parent function. Nope. Okay. Here we're going to go down to step 3. Complete the table of values for the function g of x when 2x squared is now my equation. Okay. You're going to want to grab a different color. All right. So this would be putting in negative 2 right here. What's negative 2 squared? 4. Times 2 is? Negative 1 squared is? 1. Times 2 is? 2. 0 squared is? 0. Times 2 is? 0. 1 squared is? 1 times 2 is? 2. And 2 squared is? 4. Times 2 is? 8. So now what we're going to do is we're going to graph this function. So over to negative 2, up to 8, negative 1, 2, 0, 0, 1, 2, 2, 8. What happened? It got steeper, okay. What else happened? It got skinnier. What else happened? Okay, that's what happened in the graph.
The points got
What happened in the numbers? What happened with our numbers?
bigger.
They got bigger. Okay, so how do the graphs compare? Do you think f of x was stretched or shrunk to form g of x?
Shrunk.
Raise your hand if you think stretched. Raise your hand because Logan raised his hand. Okay. Why is it stretched? You are right. Why? Who thinks they can explain it? Carter, go.
The numbers,
What about them? Tell me what you think about them.
they got more higher.
They got higher. They got bigger, right? Okay, so we're going to say, and I'm not, we're going to see this. We're saying this was stretched. Is that a true statement, what I just wrote?
Yeah.
My g of x numbers were bigger than my parent function f of x numbers.
X stayed the same, but the y got bigger.
Yep. Okay. We're now going to try this guy, step 5. What do you notice? What do you notice about my equation? What'd you say?
There's fraction.
It's a fraction now. It's a fraction. How could we list this as a, if we didn't want to use a fraction, what could I use? Could I just do 0.5? Okay, so that's fine. We're still gonna square that first. So negative 2 squared is 4 times 0.5 is 2. Multiplying by a half is the same as dividing by 2. What's 1 squared? 1. Multiplied by 0.5.
0.5.
Yep. What's my next one going to be here?
0.
0, then?
0.5.
And then
2.
2. I want you to graph those. I want you to graph those in your new color. Graph those in your new color. Yep, that 0.5 is a little hard. You can get close enough, I would think.
Make sure I get this one back, because it has my program in it for later in the year. Don't. Okay. All right, let me graph this one. Everyone should have their graphing calculator now. Let me graph this one. Negative, we shouldn't be playing with them right now. Negative 2, 2. Negative 1 and 0.5, 0, 0, and I'm just repeating on the other side. Does yours look like mine? Oops, sorry.
Yes.
Yeah? Okay, so do you think it's stretched or shrunk? And why do you say that? What got smaller?
The line.
No, I mean, the numbers, yes. Very easily, could I have stretched my lines out like that?
Yeah.
Yeah, so do I say that my lines got smaller? Did my lines actually get smaller? No. But what happened? My what got smaller?
Y.
The y, the h of x. Okay, so what I said is the numbers for h of x were smaller than the numbers for f of x. Okay. Are we understanding it a little bit so far?
Yes.
Okay. Here we go. You have graphed f of x after it was multiplied by a factor of 2 and when it was multiplied by a factor of a half. One factor stretched the graph and the other f of x and the other factor shrunk it. Use your graphing calculator or Desmos, we don't use Desmos, to graph different factors of the coefficient. What's a coefficient? We got to know what that is. What's a coefficient?
The number that goes with the variable.
The number that's in front of the variable. So 2 was a coefficient. 1/2 was a coefficient. So here's what we're going to do. Everyone grab your graphing calculator for a minute. Let me get mine up there. Turn it on. All right, and we're going to hit y equals at the top. Yes?
What do I do with all this stuff?
Hit second, quit, and clear.
Isn't it the thing that you saved for later in the year?
No, just don't give it to him. I specifically gave it to you for a reason, so it wouldn't get destroyed.
Hey, look.
Second, quit. Y equals.
Why does this look like that?
Okay, shouldn't be. I just put new batteries in
Oh,
them.
you've got stuff on
Let me see.
Mine has stuff on mine.
yours. Are we supposed to have stuff on ours?
Oh, it's just about dead. That can go like a million more times.
Are we supposed to have stuff on ours?
In your y equals, you shouldn't right now. If you do, clear it. So hit y equals. So mine's got stuff in it. I don't want stuff in it. Clear it. Clear it. On y equals. I don't want it all in there, so just stop. Okay, so y equals. All we're going to do is put in the parent function. Remember, it's x, which is right here, up at the top where you have xt. Hit x squared. And then I want you to hit graph. I don't want anything else in there. Okay? Now, what you're going to do is you're going to go back to y equals. And you're going to start playing around with it. Put different numbers in front of x squared. So maybe I type in 6x squared. Hit graph, see what happens.
Any number?
I want you to just start trying them.
It's not on here.
Clear. What? Let me see. This is why I can't sit. Can't do it.
1,356.
Don't go, yeah, don't, oh, shoot, really?
It's so skinny.
Okay, I got more. Hold on.
Doesn't work. 1,456 x squared. 56 squared. Oh. 1,235.
Oh,
X
145 doesn't make sense.
Honestly, what's the distance?
I don't think that.
35.
Wait, so we put in it over and then
100x squared.
Oh, every time.
So that's 100 and that's like right against the line.
Hey,
Uh,
you never helped me with that.
Make sure you're going back and clearing, like, don't put so many in there, clear them, but leave your x2 in there. See if you can get them to stretch, see if you can get them to shrink.
yeah, I can't get them to stretch. I can only get them to get like. I can get them to get small.
If they're going on the inside of your one that you did, that's a stretch.
I can only
If you're
get
going on the outside of the one that you did, that's a shrink.
200x squared makes it so that it doesn't even go like on the first like 5 dots.
What's that?
It starts above it.
Cream press? No, that's an everyday occurrence, sir. We got to find other times to do
It's
this.
so skinny that like it doesn't go off.
Let me see,
the
maybe
line
your window's bad.
After then.
Well, you didn't put X. Yes. No.
I'll do you
You're
one
making
better.
X in it.
Why does it look like that?
Just because it's so skinny that it doesn't.
That no, the number in front is a coefficient. You're using that number in front of it.
I put 300 squared.
So that's your parent function. Now give me another one. I want to see if you can get it to shrink and you can get it to stretch.
I don't want to get to stretch. Well, then you want to get stretch.
Yeah, how do you make it stretch?
I know how.
So stretch has got to go on the outside. No.
I already did that and it didn't work.
What happened?
Look at what we did. We already got one that's stretched.
I mean, not.
Look at our number.
Oh,
Bro,
that's
why-
your
why-
fraction.
Why's the line straight? Yeah. Why did it upside down?
0.3333.
So in every equation, you should have the x squared. Every single one of them.
I know.
I'm scared.
There's a straight
Yeah, mine's straight.
up and down.
No, like
No, then you can
X
do x squared.
0.3333.
No, you didn't. No, you didn't.
Oh, mine's upside down.
Oh,
No, you got
what did I
1
do?
squared.
Oh, mine's
x1 squared. So 1 is squared.
You must have put X squared. Yeah, mine's upside down. Wait, how do you make a stretch now again?
Nope, I just want it on the outside.
Zero.
Yeah, how are you getting to do that? That's what we're trying to figure out. Don't tell people yet.
You're supposed to tell me.
We're trying to make it so that your new graph is on the outside of your parent function graph.
I didn't.
On the outside. So when you typed in 3x, it went to the inside of your graph. I went to the outside.
I know how.
I should definitely make this by half.
Okay. Now,
I did it. Mine looks like it's fine.
how did you stretch it? Explain it to me. What did you type in? Carter, what'd you type in? Stretch. So it went on the inside.
Anything above 2.
Anything above 2? So would 1.5 wouldn't work?
I mean,
Anything above 1.
yeah, what you said.
So could I do this? Let's see. Will it go? It'll be a different color on my screen. Did it go to the inside?
Yeah.
Yes, so that was a stretch. Let's go back. Could it be 1.2 x squared?
Yeah.
Is it still on the inside? Yes. Okay. Sorry, I should be. All right. So we're just going to change it to 2 for now. How do I get it to shrink? Nathan? So any number less than what? 1. So if I do 7/8 x squared. Is it on the outside?
Yeah.
Barely. What happens if I do, this one might be easier to see. Did it work?
Yeah.
This is the easiest one to see in my opinion. Here we go. Okay. Could I keep getting it to go out further and further and further and in more and more and more? Okay. Now I know some of you did this. How did you get it to go upside down? Negative. So if I hit negative 2x squared equals, and then I graph it, it goes upside down. Could I do all of these? Negative 1/4 x2 graph. So I essentially could put all of these negative x squared upside down.
So let me ask you a question. Think about this for a minute. Put the calculators down. Hey, look at me. Would you agree that these right here, that was all dilation, right? If it was on the outside of my blue, it was a shrink. If it was on the inside of the blue, it was my stretch, right? What is this one to this one then?
It's a reflection.
Oh, it's a reflection. What's this one to this one?
Reflection.
And what's this one to this one?
Reflection.
Reflection. And what did you change? The X or the Y?
The Y.
Wait,
The Y.
can you make it-
Because you reflected over the X. So this all goes together. Yeah, it does kind of look like a spider, doesn't it?
Can you make a grass?
Yeah.
How?
Well, I will explain later. Okay. So go ahead and second. Just clear this out. Second quit. So turn it off. We save our batteries. Set them up on the side of your table, and I will be around to collect them. The clear button, the one that says clear.
You just press second off. I mean second off. Or second. She definitely hates me.
You won't, wait till I write this rule down. Okay, so our step 8. Did you try any factors that were negative? If not, try at least 2. We did. What happened to those graphs? What happened when we tried negatives? It reflects over the Okay, here's our rule that we gotta write. Let me get that back up here. So we gotta summarize what we found. A graph is stretched vertically when the function is multiplied by a factor of, or so when your coefficient is what? In order for it to be stretched, x has to be stretched. Greater than 1. Has to be. Write this down, and then you can get going. Wow, I really messed up my writing there. A graph is shrunk vertically when the function is multiplied by a factor. X has to be less than 1. Does this make sense? This is going to be very important. So if it's stretched, it's greater than 1. If it's shrunk, it's less than 1. If I were you, I would write CO6 right there. That is the rule to CO6. Okay. We're going to go back to our presentation now. Can anyone think of a real life example of when you would see dilation? Your what? Yes, that's exactly right.
Oh.
When you go to the eye doctor, sometimes you have to get your eyes dilated. And they make what happens? You look really funny too, don't you? Yeah? Your pupils get really big, right?
I don't know, I can't see other people. That's on the TV.
Well, you can't, but the doctor can.
Yeah.
Your eyes dilate bigger and smaller with a lot of different various activities, so that's a good way. Also for cops to tell if you're lying.
Your eyes dilate in your eye. When you're drunk.
What he said. Okay, so dilation, that's one of the most common real life examples. A transformation, which changes the size of a figure. But here's the thing. Okay, think about everything we've done. We've translated a figure. Like, translation just means I move it, right? Just move. Would the area or perimeter change if I translated a figure? If I moved my square from this position to this position, would the area or perimeter change?
No.
No. Okay. We've also reflected. So if I reflect the square from this side over to this side, does the area or perimeter change? No. The only one where the area and perimeter can change is a dilation, because you are physically making it bigger or smaller. Okay? It's the only time it changes. That will 110% be on ISAC. It'll ask you, it'll fill you full of a whole bunch of stuff, and they'll say the area of this square is blah, 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 and the perimeter of this square is blah, 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 blah. If it is rotated, reflected, then translated, what happens to its area? If it didn't say dilation, it didn't change. Dilation is the only one where it can change. Okay? When functions are dilated, the function is multiplied by a scale factor. You learned scale factor last year. That stretches or shrinks the graph vertically. So we already said, when you stretch it, it'll be greater than 1. When you shrink it, it will be less than 1. Okay. What time am I at? Oh, okay. We're going to start right here tomorrow.